there are some new terms that you will need to know when it comes to applying a force and deforming a material. The first term that you will need to know is what we call as stress. All right. This is not the emotional stress. This is the physics stress. This stress is defined as force acting normally per unit cross-sectional area. The normally here is talking to you about perpendicular. What do I mean by that is that if let's just say you have something like this is your cross-sectional area A, and then you have a force F acting perpendicular to the area. Stress is defined as force over area. Okay, you may notice it's a bit similar to pressure. Pressure is also force over area, right? Where we say it's force acting normally per unit area. Stress is something similar. Force acting normally per unit cross-sectional area. The ones that you did before this one was more for liquid. This is more for solid. Okay, right? The pressure equals to F over A that you've been doing a lot of. Most of them were talking about liquids. But specifically stress, force over area, this one is more for solids, particularly when you are trying to deform or extend a material. All right, so it's force acting normally per unit cross-sectional area. Normally here means perpendicular, is F over A. The units of stress would actually just be Newton per meter square or Pascal, because you know that force has unit of N, area has unit of meter square, so it's Newton per meter square. That is stress. Now this symbol here is the symbol for stress. It is the Greek letter sigma. Okay, Greek letter or symbol, whatever they call it. All right, it's the sigma symbol. Right, the sigma symbol is actually normally used to denote stress. Okay. Now, then another thing that you will need to know, another quantity that you will need to know is what we call strain. Strain is the ratio of change in length to the original length. Change in length here is E, original length here is L. Okay. So here I wrote it as extension over original length. Extension is actually change in length also. But if you want to be consistent, never mind, I just leave it as this now. If not, you can just change it to this now. Change in length E over L now. All right. If you want to change this, it's fine. If you don't want to, you want to leave it as this, it's also fine. But just know that it's defined as this. Strain is ratio of change in length to original length. When you apply a force to deform a material, apply a force onto a material, let's just say a wire, you will cause the wire to extend, correct? The wire may extend like this, giving you something like a extension E or change in length E. The original length of the material is L, okay? So if you apply a force and then the force causes the material or wire to extend by amount of E, strain is defined as the change in length to the original length or the extension to the original length. Okay, it has no units because extension has unit of meter. Original line also has unit of meter. The units will actually cancel off. Okay, so strain itself has no units because the units cancel off. All right. Now this symbol here that you see is epsilon. Okay, it looks like a tree that has been reflected or flipped over. Again, this is Greek letter also, or symbol is called epsilon. Okay, so normally when you see this symbol epsilon is used to denote strain. You see the symbol of sigma is used to denote stress. Okay, so these are two quantities that you need to know. This one is more for forces acting over an area. This is more for changes in length over the original length. All right, and then lastly, you would have something called Young's modulus. Young's modulus is denoted by the symbol E here. It is the ratio of stress to strain, sigma over epsilon. Okay. The unit is Newton per meter square or Pascal because just now you recall that stress has units of Newton per meter square. Strain has no units. So this divided by no units, obviously you just get Newton per meter square or Pascal. All right. So what is so useful about Young's modulus is this. Young's modulus, I'll just skip the one part here. I'll just go to the bottom part here. Young's modulus is actually also a measure of stiffness. Okay. Young's modulus E is also a measure of stiffness of a material, just like spring constant or constant of proportionality. Just now, earlier I said the spring constant is a measure of the stiffness of the material, right? It tells you how hard is it to deform the material. Whether are you going to need more force or less force? Or whether for the same force, are you going to get more extension or less extension, right? So in general, Young's modulus is also a measure of stiffness. The greater the value of Young's modulus, the greater stress you will need to give to produce a given extension. Now, although we said that Young's modulus is also a measure of stiffness like spring constant, Young's modulus is actually a more reliable measure of stiffness than spring constant because it doesn't depend on the size and shape of the material. It is actually the same for a specific material regardless of its size and shape. Now, constant of proportionality or spring constant will actually vary with size and shape, even though they're made of the same material. So it's not really a reliable measure of stiffness. What do I mean by that is something like this. If say, for example, I have, maybe I draw it here. If I have two different things, or rather three different things like this, I have block A, I have three different objects now, A, B, and C. They're all made of steel, all right? They're all made of steel, all right? So these three objects, you can clearly see that they are of different size and shape, right? If I were to do an experiment to find out the spring constant, Ka will not be the same as Kb. It will not be the same as Kc. The spring constant or constant of proportionality for all these three objects will be different, even though they're made of the same material. They still tell you a measure of stiffness, but because the size or shape has changed, you're getting different values. But on the other hand, if let's just say you were to do an experiment to find out what is the value of Young's modulus E, we will tell you that EA, maybe I write it somewhere else, don't have space. What we will tell you is that EA is the same as EB is the same as EC. Even though the size and shape of the material here, size and shape of the object here is different, but because they're the same material, you're gonna get the same value. That's why we call this as a more reliable measure of stiffness. All right. The concept is a bit similar to density and weight. If I tell you I have something like this, or maybe something extreme like this, I tell you all three of these is made again of steel. And then this one is object A, object B, object C. If I ask you the weight of these three objects, although they're made of the same material, you will say that WA is not the same as WB, it's not the same as WC, right? Simply because they are made of, the size and shape is different, they won't have the same weight. Okay, but if I ask you the density of the object A, B, C, because they are made of the same material, you will say that density A is the same as density B, is the same as density C, right? Correct? So it's a similar idea here, right? when you want to find out how heavy an object is, you will tend to look at the density more rather than the weight, because you know that weight sometimes can change with size and shape, even though you're talking about the same material, but density itself is the same regardless of size and shape. If you want to compare how heavy one material is versus the other, you will tend to look at density more. So something similar here. For material, when you want to see the stiffness, you will tend to look at the Young's modulus more rather than the spring constant, because you know the spring constant will tend to change with the size and shape. Okay, so that is that. Now, I mentioned just now that you can do an experiment to find out the value of Young's modulus. Yeah, you know that Young's modulus is defined as the ratio of stress and strain, but there are experiments that you can do to find out the value of Young's modulus. So that is what the next page of your notes is talking about. Okay, so when you want to find out the Young's modulus of a particular material, what you will do is that you tend to have two wires made of the same material, length and diameter that are hung from a common support. All right, your two wires are these two wires here. You hang it from the same point. Okay, one of the wire is going to be your test wire. One of your wire is going to be your control wire. All right, why do you have two wires? This one I'll explain later. For both wires, you need to use a long test wire. You use a long test wire so that you can have a large extension. The reasoning is because of this. I actually wrote it in the previous page here. You see, if Young's modulus is defined as stress over strain, and stress is force over area, and strain is extension over length, extension is in turn equals to FL over AE. If you want to have large extension, F must be large, L must be large, or A must be small, E must be small. Okay, this one is if you want to get large extension. Okay, if you want to have a large extension in your material, the force supply must be large. The length, original length of the wire must be large. The cross-sectional area must be small, and the Young's modulus of the object Young's modulus of the material must be small. Only then will you get a large extension. Okay, so right now you want to find the Young's modulus. You are purposely using a long test wire so that you can get a large extension. Because if you're talking about testing a metal, metals don't extend a lot, they extend very little. So you're trying to get a large extension as possible so that you can actually measure the extension. That's why you're using a long test wire. If you use a short test wire, your extension will be very small. You cannot really measure it. So you purposely use a long test wire in order to get a large extension so you can measure it. Okay, that's the purpose of long test wire here. And then after that, because the extension by right is going to be small in the first place, you are not going to be using a meter rule to measure the extension. Instead, you use Vernier scale, similar to a vernier caliper. You know your vernier caliper usually has two different scales, the main scale and the vernier scale. You go and slide them along, and after that you read from there the measurement. So because the extension is going to be small in the first place, you use a Vernier scale. So one part of the Vernier scale will be on one wire, the other part of the Vernier scale will be on the other wire. All right. Now, and why do you need to use two wires in the first place? I mentioned that you have one control wire and one test wire, right? Okay. The reference wire or control wire is used to eliminate any inaccuracies due to changes in temperatures or the sagging of the support. Now, you understand that wire, especially if it's made of metal, it can change length with temperature. If your temperature increases, metal will expand. If your temperature drops, metal will contract, right? So if you have a metal wire, if temperature tends to change, your length will tend to change. Right now, what you want to do is that you want to measure the extension of the wire due to a load only, due to an applied load only. You do not want the extension of a wire due to temperature. So how do you take into account the changes in length due to temperature? You have another control wire right next to your test wire. The idea is this: if this wire here extends because of temperature change, this wire will also extend because of temperature change, but your Vernier scale is attached to both. So the idea here is that whatever change you have here will also be the same change you have here. So your Vernier scale will change together with both wires. Let's just say this Vernier scale here, if your wire extends, your Vernier scale will extend also, your Vernier scale will move down a little, right? But because these two wires are made of the same material, if this extends, this will also extend. So this Vernier scale will also extend downwards. So overall, the change in length due to temperature change is offset. That's what it is supposed to be there for. That's why you have the two wires there, a control wire and a test wire. Okay, is to eliminate any inaccuracies due to changes in temperature. If this one extends together by the same amount. So your Vernier scale here will move together. Whatever temperature change, whatever changes in length due to temperature will actually be eliminated. What you measure then is actually really just the change in length due to load. Okay. So from here, you place loads onto the wire and find out the extension. You increase the load and then you find out the extension on each wire. You find out the extension for each corresponding load. All right. And then after that, you want to ensure that you have not exceeded the limit of proportionality. You want to ensure that your object still obeys Hooke's law. What you do is that you remove the load. Wait, sorry. There's a typo error here. To check that the elastic limit. Okay, sorry, I just noted there's a mistake here. To check that the elastic limit has not been exceeded, unloading is carried out to make sure that the wire returns to the original length. Okay. Just now you learned that if your elastic limit has been exceeded, if you remove the load, your material won't return to the original length. But if your elastic limit has not been exceeded, it will return back to the original length. So right now, when you test your wire, you want to ensure that you haven't gone past your elastic limit. You unload your material, see whether it goes back to the original length. If it goes back to the original length, that means you haven't exceeded the elastic limit. Okay, this is just something that you just need to know first, because some questions will ask you, how do you know whether your material has not exceeded elastic limit? So the simple answer is, you remove the load and see whether it goes back to the original length. If it does, that means you have not exceeded the elastic limit. All right. Okay, now, so here, what you do is that you are trying to find the force and the extension for many values. All right. Now, what you want to do with that is that you want to plot a graph like this. How do you get a graph like this? Is from the original equation for stress versus strain. See, stress, Young's modulus is stress over strain. Stress is force over area. Strain is extension over length. If you rearrange it, you're going to get F equals to EA over L times E. Now this one, if you try to compare with the equation of a straight line, Y being F, gradient being EA over L, E being X, you're supposed to get a graph with a straight line that passes through origin if you were to plot F against E. From here, the gradient is actually EA over L, from which you can actually find out E. E will be gradient times L over A. And then A is the cross-sectional area, is actually pi over 4d squared. L is the length of the wire that can be measured using a ruler. A is the cross-sectional area, which is given by formula pi d squared over 4. D is the diameter, which can be measured using a micrometer screw gauge. All right. So this is how you will do an experiment to find out the Young's modulus. So this one here, gradient is EA over L. Okay. So this one here, just make sure you correct the mistake. It's not limit of proportionality. It's elastic limit. Okay. So this is how you do an experiment to find out your Young's modulus. Okay, now for the same experiment where you try to apply a load onto the wire and then measure the extension, if you try to plot a graph of stress versus strain or force versus extension for that same wire under load, you will normally get a graph that is identical in shape. You see, this is a load versus extension, stress versus strain. The graph that you get normally would be identical in shape. If say your force versus extension shape is like this, your stress versus strain would also be having the same shape. All right, but the thing is that the values would be different. They won't be identical. The reasoning is because of this. You see, load is actually F, extension is actually your E. When you go to stress, it's actually F over A. And then when you go to strain, it's actually E over L. Okay? So obviously the values would be different, but the shape itself will be the same. Okay? Now from here, you can also deduce a few things. It is a bit similar to what I mentioned in the second page of your notes. The straight line portions of the graph will indicate that Hooke's law is obeyed. All right, this will mean that force is directly proportional to extension, strain is directly proportional to stress. So this are hyperbolic. Stress is proportional to strain. Okay, but it's actually the same thing. If you want to, you can actually just change it. Stress is proportional to strain. Okay, so this portion here tells you that Hooke's law is obeyed for the straight line portion. Now, beyond point P, you will notice that your graph is no longer straight. Point P is where the graph ceases to be straight. It is the limit of proportionality. Point P is where the graph ceases to be straight. It is the limit of proportionality. Okay. So beyond point P, because your graph is no longer straight, it no longer obeys Hooke's law. All right. So point P here, you can say is the limit of proportionality. Right. So up to this point here, I did the line here. I already didn't draw the line here for you. Up to here is where Hooke's law is still obeyed. Anything after Hooke's law is not obeyed. Okay. Now, so when you're talking about beyond point P, material no longer obeys Hooke's law, force is not directly proportional to extension, strain is not directly proportional to stress. Okay. And then from here, point E is the elastic limit. Up to this point, deformation of the material remains elastic. So point E is this point here that I've indicated here, this one and this one, right? So up to this point here, if you remove your load, your material will go back to its original length. So deformation is still elastic. Anything after that, beyond the elastic limit, plastic deformation will occur where the wire retains permanently some of its extension. So if you're talking about the wire here, if you go beyond E, point E, you go beyond this point, that's where you start to have plastic deformation. Okay. If you remove your load after your point E, your material will go back to its, it will try to go back to its original length, but it won't be able to go back to the original one. It will stop at somewhere here. Okay, you have some degree of permanent deformation. Here you have permanent deformation. Okay, or extension, if you would. Permanent deformation or extension. All right. So that is if you remove your load beyond point E. Okay. Yeah, and also another thing that I need to highlight to you is this. When a material behaves elastically, it doesn't necessarily need to obey Hooke's law. Okay, what do I mean by that is that, you see, in your graph, Hooke's law is up to here only, but elastic deformation is up to here. So your elastic deformation, some of it, some portion of it is where Hooke's law is still obeyed. Some part of it is where Hooke's law is no longer obeyed. Okay, so although Hooke's law is no longer obeyed after point B, the material is still behaving elastically up to point E. All right, so don't get the idea that just because something is no longer obeying Hooke's law, therefore it must be plastic deformation. No, something that does not obey Hooke's law can still behave elastically. A good example I can give you is rubber. Okay, materials like rubber do not obey Hooke's law, but they deform elastically. The force extension graph for rubber looks like this. It's a curve. All right. It's not a straight line. You won't get a straight line. You will get a curve. But this one is still elastic. Okay. If you go and do it up to here, this is your elastic limit now. Okay, up to here is elastic. Up to here is, say, plastic. So you can see from here, that this part does not obey Hooke's law because the graph is not straight. All right, but it is still elastic. Okay, so just bear this in mind. All right, just because a material no longer obeys Hooke's law, just because a material no longer obeys Hooke's law, the material must behave plastically. This one is common misunderstanding. Okay, a lot of people always think this. Just because a material is no longer obeying Hooke's law, the material must behave plastically. No, this is a common misunderstanding. You can no longer obey Hooke's law, but you can still behave elastically. All right. Rubber is a very good example. It doesn't obey Hooke's law, but it still behaves elastically. All right. So that part is okay. All right, then for the same force extension graph, there's just something else that I need to tell you. Okay, for the same force extension graph, if I talk to you about the part where it still obeys Hooke's law, all right, there are a few things you can often see from the graph. The gradient is actually force over extension. It is equals to spin constant. The gradient is actually also equals to EA over L. Because you see just now we derived the equation stress over strain is force over area X over L. So the E is FL over E. Sorry, this one I wrote it as E, right? Okay, never mind. I maintain it as this now. AX. So F is actually EA over LX. Okay. So if you have a graph of force versus extension, the gradient itself is spin constant. You can also say it's EA over L because it came from this. All right. And also in the previous chapter, you know that area under a force extension graph is actually going to be equal to strain energy. So here, area under graph is half Fx. If you know that F is actually Kx, you sub in, you get half Kx squared. So area under your graph here is strain energy is half Fx is half Kx squared. Okay, so this one is if you're talking about force extension graph. Now, what about if you get the strain versus strain graph? It's still obeying Hooke's law too. The gradient is actually stress over strain, which is Young's modulus. Okay, you see gradient here is spin constant for force versus extension. Gradient here is equals to Young's modulus for stress versus strain. Okay, and then after that here, this one sometimes does come out, but not often. The area under your graph is half stress times strain. It's actually strain energy too, but it's strain energy per unit volume. Okay, why do we call this a strain energy per unit volume? If you just analyze the units of stress strain here, unit of stress is force over area. Sorry, I do this. Unit of stress is force over area. Unit of strain is extension over L. Okay, so you get FE over AL. Now, this one is identical to work equals to force times distance. Okay, this one is identical to volume. Because if let's say I have a wire, and then I tell you I apply a force F, which in turn causes the wire to extend by a certain amount of E, and then this one being the original length L, and then this one being the cross-sectional area A, F times E represents the amount of work done to deform the material. E is the displacement, if you would, F is the applied force, so it has the unit of work, which in turn is equal to energy. And then A times L, area times length is volume, isn't it? So energy over volume gives you energy per unit volume. No? You can say that this is actually strain energy per unit volume. Okay, so if you're asked about the area under a stress strain graph, just remember it is also energy, but specifically it is strain energy per unit volume. Okay, so that part is done. This is when you're dealing with stress strain and force extension graph. Okay, the last part here is more on strain energy itself. This one is something we've learned before, so I'm just gonna breeze through this. Now, why do we say that a material when it's being deformed, or rather when the spring is being extended, has strain energy or elastic potential energy? If you consider for a spring will always try to go back to its original length. So a force must be applied to increase its extension. So when you apply a force to increase extension, you have force times displacement, you have work done. You have work done, you have energy change. And then likewise, when you have a wire that is strained by attaching a wire so that it extends, the gravitational potential energy lost by the mass is stored as elastic potential energy in the wire. What do we mean? Is something like this. If this is your wire, and then after that, you attach a mass onto it, the wire will extend due to the mass applying a force onto it. So you see your mass has actually dropped in height. There's actually a change in height. So change in height, therefore change in GPE. According to conservation of energy, if you lose energy in one form, you must gain energy in another form, right? So this GPE that's lost is actually converted to elastic potential energy of the wire. Okay, this is the GPE loss. Maybe I wrote this properly. This one is GPE loss. This is EP gain. This is for the mass. This is for the wire. Okay, so when wire is strained by attaching a mass so that it extends, the GPE lost by the mass is going to be stored as elastic potential energy of the wire. Because the mass has dropped in height, there's changes in GPE, it loses GPE. So according to conservation of energy, something else must be gained. Your energy gain is EPE of the wire. Okay, so this energy that is gained by the wire or spring is known as strain energy. All right, which will be recovered when your material returns back to its original length. In both cases, for the spring and the wire, you are actually doing work to deform the material. Okay, when you remove the load, the material returns back to its original length. You're going to recover back that energy or the work that you did. If you apply some sort of work, if you did some sort of work to stretch the spring, you remove the load, the work will be recovered, the energy will be recovered. If you apply a load onto a wire, you remove the load, the wire will go back to its original length, you recover back the work done or the energy stored. Okay, so strain energy stored in a spring or wire is equal to the force extension graph. This one we know already. Area under a stress strain graph is equals to strain energy per unit volume. This one again we already know. So this is actually just a recap of whatever we've done so far. If your wire obeys Hooke's law, your force extension graph looks like this. It's a straight line that passes through origin. So strain energy is area under the graph. It's going to be half Fx. If you sub in the Hooke's law, F equals to Kx, you're going to get half Kx squared. Both of these is to find strain energy, provided Hooke's law is obeyed. Okay? Meaning to say it's a straight line. Only then can you use this. But in the case where your Hooke's law is not obeyed, where you get something like this, you cannot use F equals to, you cannot use half Fx, you cannot use half Kx squared. Strain energy is just area under the graph here. Okay, so that part is all right. Huh? Okay, then after that, the last part will be what you see here. If you have a ductile material that is stretched by a tensile force to a point beyond its elastic limit and then reduced to zero, what do the areas X, Y, Z represent in the force extension graph? So let me just highlight to you. This is the force extension graph of a wire ductile material where you apply a tensile force. You stretch it beyond its elastic limit before removing the force. All right, what do arrows X, Y, and Z represent? This part here represents the loading of your wire. This part here represents the unloading of your wire. Okay. This part here represents the unloading of your wire. If you're talking about, if you remember that area under the graph represents strain energy, or rather the work done to, or rather the work done on the material, what do the areas now represent if I were to separate them off into X, Y, and Z? Now, area X, Y, Z is actually this entire thing, right? You can just think of it as being something similar to this. Okay. Area XYZ represents the work done to stretch the material during loading of the material. Energy is stored in the material during this stretching as EPE or strain energy. Okay, this is what area XYZ represents. Now, what about if I ask you what is area Z itself? Area Z is going to be this part. Okay. Now, area Z represents, you see, area Z is this one. Then I redraw it for you. It's actually representing this part here during the unloading. So that area Z that you have here is actually the work or energy recovered from the material during unloading. Remember that I mentioned to you, if you remove the load, your material will try to go back to its original length. During the time that it goes back to its original length, whatever work that you have done onto the material, whatever energy that has been stored will be released back. So over here right now, your area Z here is actually the representing the energy or work that will be recovered from the material during unloading. Specifically, is also the maximum EPE that can be stored inside the material. All right, because this is the amount that you can recover back. So this is the maximum elastic potential energy that can be stored in the material. All right. So then the next one will be, what is area X plus Y? Area X plus Y is this one here. Okay. Area X plus Y is this one. Okay. What does this area X plus Y represent? This like this. Like this, it is representing this one. Okay, that one represents the network done on the material to permanently stretch it. You notice that the question already told you that you have exceeded your elastic limit. You stretch your material beyond your elastic limit, and then after that you remove your force. You will understand that from there, if you remove your force, you're going to have some sort of permanent extension. So what's happening here is that you see this portion here. This portion here is actually your permanent extension. Okay, this area represents the network that has been done to permanently extend the material, to permanently stretch the material. Okay, so try to deduce what each area means. First one, XYZ, just tells you the amount of material that you, the amount of work that you have done to stretch the material. This is the amount of energy that has been stored in the material. And then after that, area Z is actually the amount of energy or work that you can recover back from the material during unloading. Then area X plus Y here is the amount of net work that you have done to permanently stretch the material. Okay, that's what those little areas there mean. Okay, then the last one is this one. This one is for rubber band. Okay, rubber band that is stretched and then relaxed to its original length. Okay, so a rubber band is stretched and then relaxed to its original length. The force, as the force is increased, the curve follows path OPQ like this to extension E. And then when the force is reduced to 0, the curve follows path QRO as shown here. All right. The arrow label X is this part here, and then the arrow label Y is this part here. Okay. So what do the arrows X and Y in general represent? So if you're talking about, say, area X plus Y, which is actually this entire area here, you can think of this little portion here as loading, and then this portion here as unloading. Okay, so you're talking about the entire area below the graph here. This is actually the work done to stretch material during loading with the energy stored in material during stretching. It's the same as what you see here in the previous example, XYZ. This whole area here represents the total amount of work that you've done to stretch the material. Okay, so you go to the second one. What does area Y itself represent? Area Y is this one. Okay, this one was just now the loading. This part here is unloading when you remove your material, remove your load. So this entire area here actually represents the work energy recovered from the material during unloading. Similar to area Z in the previous example. Okay. Okay, is the area under your unloading part. Then after that, what is area X? Area X, this one is loading, and then this one is unloading. Area X is this one. Okay, what does this area here represent? Okay, now the first two areas, you will have noticed that there's a similarity with the previous example. The first one is saying that work done to stretch the material. Second one is work recovered during unloading. Now, the third one here that you see for this current example will not be the same as the previous example. Okay, here we said that area X plus Y was the work done to permanently stretch the material. Over here, this one, you had permanent extension. The current one that you see, there is no permanent extension, right? You see, you went off from here to here, and then you went back to your original length. You have no permanent extension. So whatever area that you have here in between, you cannot say it as the work done to permanently stretch the material, because in the first place, your graph here does not have any permanent extension. This one here has no plastic deformation, only elastic deformation. Okay, so what does this area mean? This one here is actually the work or energy loss from the material during unloading in the form of heat. Okay, so this area X here represents the energy that you've lost in the form of heat. If you take a rubber band and then you try to stretch it and unstretch it many times, you will notice that your rubber band will tend to heat up. That is this part here. Because when you stretch it and unstretch it, you will tend to lose some energy. And then that energy is in the form of heat. So if you stretch and unstretch it continuously, you take a rubber band, continuously stretch and unstretch it, you will feel that the rubber band becomes hot. It's because of this thing here. Okay, when you stretch and unstretch it, there will be some amount of heat loss represented by this area here. Okay, that is energy loss as heat for this part. In the previous one, the previous example, this one also represents something, but it's not energy loss as heat. It's the net work done to permanently stretch the material. Okay, so this material has plastic deformation. Okay, right. So this is everything that you need to know for deformation of solids.